Hey there, welcome back. We're doing 7B. We're learning to count. Shouldn't be that easy. And we're also going to be combining probability. Probability. Hey, I'm doing better than I did the other night. Well, let's get right down to it. This is my favorite example of all time. Let's say you have women and you have smokers. So W means women. W stands for women. W complement, meaning opposite of women, meaning not women are men. So guys, you don't get your own letter. We're just W complements. And then there's smokers. And there's complement of smokers, meaning not smokers. And there's 4 distinct zones here. We got women who smoke. Maybe there's 100 people. You're at an establishment. And let's say 10 of them are women that smoke. And let's say that there's 25 smokers who are not women. Ooh, these are male smokers. And over here are women who are not smokers. And where is the zone of non-smoking men? Well, we know there's 45, 55, 65, 70. There must be 30 outside the women's circle, outside the smoker circle, and basically we got 30 men who smoke. Now, I have run across this in real life, not math life. This is quite common. So we got women and we have not women. We got smokers and we have not smokers. And this is my overlap area, my and area. So this is smokers and women. Ooh, and I always go like extra columns because this is so cool. So these are my 4 zones. These are women and smokers. There's 10 of them. These are women and not smokers. So here's the women and not smokers, 35. Okay, the W complements, just say you're men. So outside the women's circle, there's 2 numbers. You got smoking men, 25, and you got non-smoking men, 30. Now the cool thing about this table is self-tabulating. Adam, 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 100. Now it's just cool because this happens in real life. You got women with credit cards. You got men with things. This is very typical, very common type of situation. This also has like what I want to call the AND table, and it's self-tabulating, which I find really cool because now I know there's 35 smokers, and I can see there's 35 smokers. I know there's non-smokers to be 65, so outside the smoking circle, there's 65. It's a really good thing. Like 55, well, there's 55 men. Meaning outside the women's circle, there's 55 men and 100 total. This thing is awesome. So I can ask you probability questions now, and then we can score a whole bunch of points. What's the probability of women and a smoker? Well, you go, well, there's 100 people. So women and smokers 10. Reduces to 1/10, or 0.10. Great question. Ask me any and question you want. What's the probability of being a non-woman, a W complement, really meaning a man, and a smoker. Well, guess what? We know there's 100 people. And how many of these are there? W complement overlap with 25. 1/4. But the or question is really tough. And when there's overlap in my sets and somebody asks me an or question, all of a sudden I'm not very smart. But you're in luck. There's a formula. So you add up the women and the smokers, but you take away the probability of being a woman and a smoker. And that's our formula. So the cool thing is, I can do this problem now. And I'll explain how, like, really smart people do it, but unfortunately I'm not really smart. I don't handle or questions very well. So probability of being a woman in this situation, probability of being a woman is 45 out of 100. Plus the probability of being a smoker is 35 out of 100 minus probability of being a woman and a smoker. We already did that. That's 10 out of 100. And since it has the same common denominators, you get 80 minus 10 is 70, or 7/10, or 0.7. Now, I needed the formula because I know enough to be scared in probability when you got things that are overlapping. And they asked me the or question. I don't do that well. But let's try to do it like the smart people. They drive me crazy. So you got women, you see there's 45 of them. And you got smokers, and you see there's 35 of them. So a lot of people just want to go 45 plus 35 is 80 out of 100. But here's the deal. I counted this 10 twice. Because I got 35 plus 10 is 45, and 25 plus 10 is 35. You can't count the 10 twice. So if you really want to do it correctly, you just say, oh yeah, I got my women, got my smokers. I obviously counted 10 twice. So 45 and 35 is 80, but I got to subtract 10. And that's what the formula says to do exactly. So yes, I'm jealous that people can just look at it, yell out the answer, but hey, I'm a little slower, so I need a formula. That's the hard part of the lecture today. Now, when you got non-overlapping sets, some set A, some set B, then the probability of A or B is just the probability of A plus the probability of B. Really easy to do an OR problem when I have no overlap. So the trick is trying to decide if you have overlapping events or non-overlapping events. So what is the probability of rolling a 2 or a 3? Well, how can you overlap a 2 or a 3? You can't roll a 2.5. No, it's not going to happen. A 2 is different from a 3. They have nothing in common, so it's the probability of 2 plus the probability of rolling a 3. Well, it's 1/6 plus 1/6, assuming we're rolling a die anyway, 6-sided die, which is 2/6, which is 1/3, which is 0.3333333. Now, deck of cards. You got a queen, and another is a club. clover, whatever. 3-leaf clover. I'm terrible. So you want to draw, suppose you have a standard deck of 52 cards. So cards, 52. What is the probability of drawing a club or a queen? One problem, there's the queen of clubs, there's the queen of spades, there's the queen of hearts, and there's the queen of diamonds. There is overlap because there is a queen of clubs. But that's okay, because I got a formula that says it's the probability of being a club plus the probability of being a queen minus the probability of being a queen and a club. So here we go. What is the probability? Wish I would have saved some more space. Poor management. Probability of being a club. Well, there's 13 clubs out of 52. Or you could have went with the old, there's one of 4 different suits. Plus the probability of being a queen, 4 out of 52. Because there's 4 queens of 52. Minus my favorite. What's the probability of drawing a queen and a club, i.e. the queen of clubs? 1 out of 52, which is 17/16 of 52, and 8/26, ouch, 4/13, and then you could give me a decimal. Now, the book does the problem. I did the smoking women or the women smoker problem. Kind of how you want to phrase that. One sounds better than the other. They talk about women or Democrats. So obviously it's just like the smoking women problem, the women smoker problem. So we're not going to work on that because I already did one that's just like that. So we got to work on this other topic. So it's called the at least once rule. I think this book just makes up stuff like I make up stuff. Kind of like it sometimes. But they're doing this problem where they're throwing 3 coins. 4 coins. Oh man. So this is going to take some space. Head, tail. Head, tail. Head, tail. Head, tail. Head, tail. You don't have to do this. Head, tail. 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 And there's 16 outcomes. You can see it because there's 2, 2, 2, and 2. By the multiplication rule of probability, 2 times 2 times 2 times 2 is 16. And I actually know what all 16 of them are because I brute forced that bad boy out. Head, 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 tail, head, etc. Now, what are they getting at here? They want to talk about the at least statement. The probability of at least one head in 4 tosses. Whoa. Now, a fancy way of saying that is the probability of one head plus the probability of two heads plus the probability of three heads plus the probability of four heads. And I don't know about you, but I'm thinking about finding the probability of zero heads, which is tail, 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 which is 1 out of 16. And, you know, so I'm thinking the answer is 15 out of 16. But anyway, let's give the book a chance. So what the book says then is the probability of at least one head plus the probability of no heads has to add to 1 because that's the only two things that can happen. So they're saying the probability of at least one head equals 1 minus the probability of no heads. And that's exactly what I was saying. So what I'm getting at is I know the answer to the problem is 1 minus tail, 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 1 out of 16, and that's going to be 15 over 16. But yet the book goes on, and they go, what's the probability of no heads? So they start focusing on this thing, and they're trying to get all theoretical here. Well, it's probability of not a head on toss 1 plus the probability of not head on toss 2 plus the probability of not head on toss 3 plus the probability of not head on toss 4. But we know this. The probability of not a head is 1/2. Oops, sorry. These are times. So the probability of no heads is the probability of a not a head on toss 1, and and's going to be multiplied times the probability of not head on toss 2 times the probability of not head on times 3 times the probability of not head. So you get 1/2 times 1/2 times 1/2 times 1/2 is 1/16. So they're trying to get clever. They're saying, hey, Verbsky, you don't have to draw the tree. I knew that there's one chance out of 16 because I can see there's one chance out of 16, but 1/2 times 1/2 times 1/2 times 1/2 is 1/16. So what they're saying is, what we're going to do is we're going to take this formula and come up with something really cool. So the probability of at least one event A in n trials is 1 minus the probability of not A to the n. So bottom line, what they're doing is they're giving you this really cool formula to do problems very similar to this. So here we go. They're going to ask a question. In this case, okay, so use the at least once rule to find the probability of at least one head when you toss 3 coins. What's the probability of at least one head when you toss 3 coins? Well, that's 1 minus the probability of not head to the 3. But what's the probability of not ahead? Well, that means the probability of getting the tail, and the probability of getting the tail is 1/2 cubed, 1 minus 1/2 times 1/2 times 1/2 is 1 minus 1/8, which is 8 over 8 minus 1/8, 7 over 8. Life's good. We use the at least one rule. It's pretty cool. So, let's do another. Playing lotto. You purchase 10 lottery tickets. 10 lottery tickets. So the probability of a win is 1 in 10. You know what they mean? 1/10. Therefore, the probability of a loss is 9 in 10, which is 9/10. What is the probability of at least one winner? Well, you know what it is? It's 1 minus the probability of no winner raised to the 10th. 1 minus 0.9 raised to the 10th. Get out your calculator, 0.651. So, bottom line, I'm done in 22 minutes. I run out of book. It's all that's there. So, compared to the last section, section's pretty good. It's looking like they're going to be really testing over maybe like 2 or 3 things. So, if you ask me, section 7B is a really good section. That's it, guys. End of story.